All right, so here we are with the 10 formulas for circles and regular polygons. Again, a lot of this has been touched on in the circle project, the magic circle project. So hopefully this is a little bit more review. But again, remember that a lot of the solving that we're doing ends up being kind of backwards from just plugging them in. So either way, first thing we're going to look at here is a definition of a circle. So a circle is the locus, meaning kind of the set of points in a plane that are fixed, a fixed distance, which would be your radius, from a point called the center of the circle. So here we are with the center of the circle. Your circle is named by that center. So circle P would mean that there is a P in the middle here. And so again, the locus is the set of points, and the fixed distance is your radius. All right, so then we have the area of a circle formula, and again, you most likely have written this down in your magic circle project, but we also have it here. So pi r squared, and of course r is your radius from the center out to the end of the circumference. And then we have our circumference formula, which can be given in two ways. I tend to do 2 pi r because then every time that I'm looking at a circle formula, I always am searching for an r. Versus there are those that use pi d just because it has less variables. But then you kind of have to know, am I looking for the diameter or the radius, and which formula am I using? So I try to just keep everything in radius. All right, so in our first example, we need to find the area of circle P with a radius of 16, and notice that it says in terms of pi. So some of these will say round to the 10th place or whatever, but in this case, they want you to basically just give them the answer so that there's a pi sitting there still. So area of a circle is pi r squared, and every time that you solve something with geometry, it's best if you just start by writing the formula as it is. And then the next thing that we're going to do is plug in a 16 for the radius. So double checking that that's the radius and not the diameter. And so in that case, we are going to have 16 squared, which is 256. So we have pi times 256. But remember that they want it in terms of pi, so don't multiply by pi here. Instead, just take the idea that usually this is considered kind of a variable. So instead, we would say 256 pi at the end instead of in the front. But of course, both are correct because it's still multiplication. So 256 pi is the area. It doesn't, it says centimeters, so we do want to put that there is a unit, and since it's area, that it's squared. So that's our first use of one of these formulas. Moving on to example 2, we're finding the radius of circle X, in which the circumference is 24 pi inches. All right. So notice again that we're trying to find radius and not circumference. We're using circumference to work backwards. So I'm going to use 2 pi r because, of course, I'm trying to find the radius. I don't really want to use the one that asks for a diameter. And then 24 pi is what the result is going to be. So now I just get to solve for r. And what's unique about this is that we get to actually just cancel out our pi right away. Notice that everything is multiplied. So I can just divide by pi right at the beginning and get 24 equal to 2r. And so then taking away our 2 so that we can get r. Gives you a 12 for your radius. And again, if you didn't need to show work for that, I understand, but 12 is the inches that we are looking for. And of course, it's a distance, so it's not inches squared. The next one here is example 3, and we're finding the circumference of a circle in which the area is given. So we're going to have to work backwards from area to get radius, and then plug that radius into circumference. So our area at first comes from pi r squared, but they're telling us that the area is 9x squared pi. So again, we are trying to find r squared, so let's go ahead and divide everything by pi, because that makes everything a little bit easier to look at without decimals and things like that. So we'll have 9x squared, which is going to be r squared. And so then we just need to understand pretty much what the square root of this side is. So looking at that left side there, we can technically take the square root of both sides. And that means that we would get a radius of the square root of 9, which is 3, and the square root of x squared, which is x. So in that case, our radius is 3x. But remember that that's not the end result. The end result is plugging it into circumference. So they're just getting you to do 2 problems in one. So tricky. So again, since we know that the radius is 3x, we can go ahead and put 3x in for the r. It doesn't say necessarily to keep it in terms of pi or anything like that. So we will, in fact, evaluate this. So let's see, 2 times 3 is going to be 6. And since this is all technically just multiplied out, it doesn't matter in which order you do it since it's all multiplication. So that means that there's 6. And then at least the way that they wrote it here, they did the variable and then the, what's it called, the pi. So in that case, 6x pi could potentially be our answer if in terms of pi. But if you don't like that, you can also do 6 times pi since it doesn't suggest how to do it. And so 6 times pi is going to be 18.8496. That's that one. And then, of course, the x with it as well. I'm going to just keep this one because it looks a little less sloppy. So 6x pi as the circumference. All right. Oh, and then it's a circumference, so it's a distance, so centimeters. Okay. Then looking for our next sheet. There it is. All right. So then the next thing other than circles is the fact that we're basically doing a circle with a polygon inside of it. So we still have this center point. We still have a radius, okay? But the center of a regular polygon is equidistant from the vertices. So remember that a vertice, for instance, is W, and the center is C. And so again, this is your radius that is, notice all the tick marks, the same length from the center to every vertex. All right. The apothem, and yes, that's what it's called. So your apothem here is the height of each of these triangles. So if you draw every radius in a regular polygon, the height of each of those triangles that you've just made, which are isosceles, but could also be equilateral, not in this case, but it's the distance from the center of the polygon to the center of the polygon side. So notice that I labeled this one as M because it's actually the midpoint. So all of these are the same lengths for radius, but YM to MX is also the same length because this is a height of this triangle, and it would, for an isosceles triangle, be at the midpoint. So CM is the height. And then the central angle of a regular polygon has its vertex at the center and its sides pass, that's grammatically incorrect, and its sides pass through consecutive vertices. So the central angle, again, is something like this, all right? So all it means is that it's from the center and it has 2 radius as its kind of rays going out from it. So, and hopefully that makes sense from chapter 12 that that's your center. Okay, so the formulas here come from kind of this main diagram here where we're just really focusing on the apothem and the fact that the radius goes from the center to a vertex, and that we label each of these sides as S, just as we did in a square. So the area of a regular polygon, and again, you probably did this in your magic circle project, but the area is going to be 1/2 times the apothem times the perimeter. perimeter. I can totally spell parameter. Okay, and of course, in order to get your perimeter, you're going to go ahead and, I'll mention this is A, you're going to take S times the number of sides, so in this case, times 5. Then, to find the area of one triangle, because that's actually how you're doing it in each of these, to find the area of one triangle, you're going to have a half base times height, but the base is your side length, and the height is your apothem. So if you ever need to kind of figure that one out so that you can then multiply by 5 or however many triangles there are in there. So, of course, we're going to use this formula. So we're going to find the area of a regular hexagon. And notice there's a lot of space because it does take a minute here. Regular hexagon with side lengths of 6 meters. So since they don't necessarily have a picture here, we do have to remember that hexagons have 6 sides. All right, so hexagon here. And that's not necessarily regular, but it is if I put little tick marks on it. So there's our hexagon. It also said that all the side lengths are 6 meters. So we'll go ahead and label that. And now we want to find the area. So we need to find the apothem and we need to find the perimeter. Perimeter is not so bad because in this case, it's going to be 6 sides times the length of each of the sides, which is 6 meters. So your perimeter is just 6 times 6, and so 36 meters is your perimeter. All right. However, the apothem is the one that's a little bit more tricky. So remember that the apothem is from this center to the center of this outer piece here. And so we can put in our radii here to kind of make a triangle that exists. All right. So I'm going to kind of expand that triangle there. And label this as the height or the apothem. All right. This down here is your side length, which we know is 6 meters. But remember, and this is a radius, so it's the same length here and here, so that's good to know, because that's an isosceles triangle. And hopefully, remembering back to our chapter on triangles, or all of the chapters on triangles, we know that that height then cuts this angle in half. It also cuts this side in half as well. So that means that this central angle, which we find by taking the fact that this was 360 degrees all around this center, but we're going to take it and divide by the fact that we are going to make 6 triangles. So each of those 6 triangles has a central angle measure. And so that means that each of them is 60 degrees. So a few things to get from that. If this is 60 degrees and these two sides are the same, these are also actually 60 degrees down here. So we do know that other than just an isosceles triangle, this is actually an equilateral triangle. However, when you take this triangle and you actually cut it in half again, so lots of cutting, or zooming, I guess. We still have your apothem, but now instead of having 6 meters, remember that this side length was the same as this side length. So this is actually 3 meters. It's going to be half of it. We know that this is 30 degrees because 60 was cut in half. We know that this is 60 degrees because we said that it's an isosceles triangle. And so the base angles are the same. And then we know that this is the radius, but also the hypotenuse. And so on that note, if that's the hypotenuse, then we also have, if we're staring at or standing at this angle, we also have this as an opposite side. And so hopefully you can see where we're going with this, and this as an adjacent side. All right. And so in order to get this adjacent side length and the fact that I have an opposite measurement, I'm going to use tangent. Because remember that tangent of whatever angle it is going to equal the opposite over the adjacent. So as much as you thought that trig might be over, it turns out that we get to use tangent here in order to figure out what our apothem length is. So remember that tangent of our angle measure is going to be opposite over adjacent. So technically that means that tangent of 30 degrees. And so you're asking, why are we not using 60? I just claim to usually use this one up here because it's the easiest to find. It's half of the angle that you already had. Okay, so rather than taking the time to kind of get this one, just pick one of the angles, of course, not the 90-degree angle ever, and use it and then label opposites and adjacents by it. So tangent of 30 is going to equal our opposite, which is 3, over our adjacent, which we don't know, but it's the apothem. And so we just need to solve this in order to get our answer. So kind of ran out of room here, so I'm going to rewrite it over here. Tangent of 30 equals 3 over a. And so in order to solve that, remember this is a proportion. And so I'm going to multiply 3 times a for cross multiplying. So sorry, 3 times 1. And then tangent of 30 times a. All right. And so that means that 3 is going to equal the tangent of 30. So let's see what the tangent of 30 is. You're not going to get the same tangent of 30 if you aren't in degree mode. So make sure your calculator is in the mode of degree versus radian. And so in that case, you get 88.10. And that's being multiplied by a. So go ahead and divide by 88.10. And we're going to get an a value of something good. Oh, I did tangent inverse. Whoa. No wonder that number was huge. Okay. This number is 0.5774. Sorry, I did tangent inverse, so you really weren't going to get what I had rather than just tangent. All right, so in that case, we're dividing by this 0.05574. And so 3 divided by that is going to leave us with 5.1962 for an apothem. So we know that our perimeter is 36. We know that our apothem is 5.1962. And so now we can plug it into our formula up here. So that means that our area is going to be a half times the apothem, which is 5.1962. And then times our perimeter, which is 36. It does say round to the nearest tenth, so when we multiply each of these values out, we're going to round to 1 decimal place. So 5.1962 and 36. So we are going to get 93.5, and then the units are meters, and we are doing area, so meters squared. So do you need to do this for every single problem? Pretty darn much, okay? Anytime that you are trying to find the apothem, you are going to use this idea of tangent of that upper angle, which is half of the central angle, is going to equal the opposite, which is half of your side length over the apothem. So you are going to have to use tangent pretty much every time. And then your perimeter, of course, is the multiplication of each of those. So sometimes instead of given a side length, you might in fact be given the apothem. So that's going to be working backwards from apothem to get side length, which would also use tangent. So pretty much using tangent every single time. All right, so now we have two more examples that are working through this. So again, notice that this one is a side length, so we are going to do the same process here. We're going to find the perimeter. We're going to draw our original image, zoom in to the isosceles triangle, and then zoom into the right triangle. So we have a pentagon here, and a pentagon is going to be 5 sides. And the side length is 8 for your side length, and we're rounding to the nearest tenth. So I'm going to start by drawing my image over here. Oh man, that's a super pentagon. So in that case, I am mentioning that each of these sides are the same, and the reason we know that is because of the word regular. So that means that everything is the same length. And so we now have a pentagon, and each of the side lengths is 8 inches. But then, of course, we are going to have to try to find the apothem. And remember, the apothem is from the center to the center of the opposite side. And that then breaks this piece into 2 equal sides. And also these radius or radii form a central angle. All right, and that central angle, if we zoom in, so again, now we have this isosceles triangle with a height of an apothem, and these two sides broken in half. It was 8 inches, and so this is going to be 4 inches and 4 inches for the fact that the whole thing used to be 8. We also know this central angle, and it's going to come from taking the fact that it used to be 360 and divide by 5 this time, because there are 5 sides versus our last example, which was 6. And so now we have our right triangle that we're going to end up using tangent and trig. And so 360 divided by 5 makes that central angle a 72 degrees. But then, of course, to get this angle, we now need to do 72 divided by 2. And so 72 divided by 2 is going to leave us with 36 degrees up here in the corner. We also know that this is the apothem, and then we know that this side length is 4. So hopefully this brings you back to your trig where you were given an angle, which we now know is 36, an adjacent side, and an opposite side length. And so to find the apothem, because again we're trying to find the area, it's going to be a half apothem times perimeter, so we need apothem. We're going to use our trig. So the trig to solve this says that we're going to do tangent of an angle, and that's going to equal the opposite over the adjacent. If we fill in those pieces, that means that we're going to do tangent of 36 degrees, and that's going to equal our opposite, which is 4, over our adjacent, which is A. This one is going to be solved the same way as the previous one, and so all you need to do is set it up as a proportion, multiply your 4 times 1, and set that equal to tangent of 36 times A. So 4 is going to equal the tangent, not the tangent inverse as I did last time. Tangent of 36 is 0.7265. And then we'll have to divide by that decimal. In order to get our apothem all by itself. So 4 divided by that decimal gives you 5.5055. It's a lot of 5s. All right, so if that's our apothem, we now up here in our area can plug in that the apothem is this 5's digit. Oops. 5.5055. And then your perimeter is going to be the fact that there are 5 sides times a measurement of 8 inches for each side. And so 5 times 8 is 40 inches for your perimeter. And so we'll multiply that by 40, and now we can actually get our area. So area takes a half times 5.5055. And our 40 for the perimeter. And so now we know that it's 110.11, and this is an area. It says round to the nearest tenth, so I guess we don't really need this one. And so we'll change that into our I for inches. All right, and so that's our area, rounded to the nearest tenth, and putting our answer here. Oh, and I didn't put squared even though it's an area, so squared. All right. So again, drawing a picture, very helpful. Drawing the one isosceles triangle and then drawing the right triangle is going to help you figure out where your tangent is. And of course, there is a pattern for this. And so once you get into that pattern, you'll realize how to do each one. And so that was our last example. You do have an assignment for this section, so go ahead and try that out. It's not too many problems. And of course, there will be a video answer to check out as well.